For the first part of this lesson, we are going to just take a little bit of time to color code a periodic table according to the families that exist on the periodic table. And so this is something, again, we have talked about in the past, but now the important part is we understand a little bit more the role that the valence electrons have, and we're going to continue to develop that over the course of this class. When I start to talk about the reactivity of the alkali metals with the halogens, I would love for everyone to just know where those are located on the periodic table. And then you can look and see, oh, the alkali metals have 1 valence electron, the halogens have 7, so it makes a lot of sense why and how they would interact. So that's the kind of purpose of this. For the remainder of this part of the video, I'm just going to go through color coding this out. I'll add a little bit of information, but really the information about the families themselves will come in the second part of the video. So starting off with hydrogen, I'm not even going to color code it. Hydrogen is its own family on the periodic table. It gets its own classification just because it is involved in so many different compounds that are formed, and it really does its own thing in comparison to other elements. The next one, which is in the same column as hydrogen, are the alkali metals. So I'm going to go ahead and highlight that. And alkali metals will be everything underneath hydrogen all the way down to francium. Again, we'll get into specific details about what that family entails. Our next one are called the alkaline earth metals, or sometimes people just shorten that up and say alkaline metals. And that's going to be the beryllium through radium column. Our next one, which we've been referring to as the transition metals for quite a long time, are those D block elements. So going through and highlighting scandium down to lawrencium and then all the way across. So just kind of color code in that portion. Again, feel free to pick the colors that you prefer, the ones that you can easily see, easily distinguish. So our transition elements are also referred to as the D block elements. Okay, before we go into the next part, which is post-transition metals, metalloids, one of the things that I need you guys to do is go ahead and draw in your staircase. Now, when we identify the metalloids, I'm actually going to add something here. So metalloids / semimetals. They're referred to as both. I actually probably refer to them as semimetals more than I refer to them as metalloids, just as a heads up. I'm going to go ahead and color code those a gray color. So that starts with boron, and then silicon, germanium, arsenic, antimony, tellurium, polonium. So those will be our semimetals. And then once I have that group, that family labeled, then I can easily go back and fill in my post-transition metals, which is everything else that's left. So that aluminum, gallium, indium, thallium, just kind of go through here, tin, lead, bismuth, and it would include anything that, we know that this row is filled. This is a older periodic table. Only reason why I didn't switch it out from older pictures is it doesn't really matter. Those, all the way through 118, we don't typically, discuss those at all, simply because they're so, they have to be created in a lab and they only exist for fractions of time. And so they're not usable to us in anything that we do in an intro chemistry lab. Definitely great learning opportunity there, but it's nothing that is usable for us at this level yet. Okay, so going on to the next group, which is halogens. Halogens being a super reactive group on the periodic table, involved in both ionic and covalent compound formation. Noble gases, we consider those to be our most unreactive elements on the periodic table. And that's kind of a misnomer because these things can react. It's just they typically aren't reacting under standard conditions. Then we have the lanthanide series, which is very easy to find. It's one of the things I like about it is you can tell that it's the lanthanide series because, well, in this one it's labeled, but it also starts with lanthanum. And then we also have the actinide series. And then last but certainly not least, we have these things that were classified as other non-metals. So you have carbon, nitrogen, oxygen, phosphorus, sulfur, and selenium. So interestingly enough, they're just referred to as other non-metals, but if you look at carbon, nitrogen, oxygen, phosphorus, sulfur, those are some of the key elements of life. So I kind of like to refer to them as our major elements of life, but they just in chemistry didn't get a very fancy designation. So that's the color coding that I want you guys to match up with. And honestly, starting to memorize those locations would be good, simply because I do reference them often with respect to their names moving forward. So again, it's just kind of beneficial for you to get a good feel or a good sense for where they are on the periodic table. Now that we have the periodic table color-coded with the major families, the purpose of the next portion of this video is just to learn some of the basic properties, both physical and then chemical, of the families that are there. We're going to highlight some of the more important ones. I mean, there's a lot here to remember, and we're not going to get into all of the details for every single element or every single family, but there are going to be some things that will be really obvious to you, and then some other things that are worth highlighting to make sure that you remember those in the future. So we're actually going to start with the alkali metals, and I think that they're pretty cool. You don't get to really play around with them much in class, though you will get to experience some of them. So we do have some lithium and sodium on hand, and then on occasion we get some potassium. One of the reasons that we don't have major storages of these in class, and then also we don't have access to some of the ones lower, is that they blow up, or they don't blow up, but they tend to react very rigorously when you place them in water. And that would be considered a chemical property. So I'm going to highlight that one on here. When it reacts with the water, it actually breaks apart the water molecules and it will form hydrogen gas. And then the other thing that's left over are the hydroxide ions. So I'm going to actually just take a minute here to draw something. So you add something like sodium to the water and it has 1 electron. And in that chemical reaction, it's reacting with hydrogen and hydroxide, right? So it's reacting with water. It breaks that apart, and when it breaks that apart, just something kind of cool, what ends up happening essentially is you've got this OH minus ion. This electron here actually goes to the hydrogen, and this is going to come over here. Because then sodium lost its electron, it becomes a positive. And so now we have a couple of things at play. The sodium, which is positive, can then be attracted to the hydroxide, which is negative, and then that's going to form sodium hydroxide, so that's going to be the base. Then we've got these free-floating hydrogens around, and it's not like you just have one. You have lots of these. And then those will bond together, it forms a single bond. And this is what is forming the hydrogen gas. So you see this happen instantaneously. So the second that you put a piece of lithium or sodium, any of the alkali metals into water, you have this immediate and rapid reaction. So you have hydrogen gas being rapidly produced. Well, one of the things that we'll talk about again at the end of this is that hydrogen gas is inflammable, meaning that is highly explosive. So you always have to be really careful when you're working with these substances. Now, one of the things that can happen is that there's a lot of heat generated in this process. There's a lot of energy. So if you have too big of a piece and you put it into water, it will start to react. It releases the H2 gas and it gets really hot. And one of the things that can happen is it can actually ignite the hydrogen gas, and you can have a major explosion on your hands potentially. So really kind of cool, fun, especially for those people who are in chemistry, to learn more about the explosion parts of this. When we come back to school in a month or so, this is one of those labs that is always kind of fun. You get to look at a lot of different chemical reactions, and we do look at the reactivity of these elements. Again, as a high school science teacher, I have access to some things that other people wouldn't normally have access to, but I definitely don't have it in large quantities. I wouldn't want to be responsible for that. Okay, I am going to hop back on my computer here for a second, and then we'll continue. So one of the things that we already know about alkali metals, and I just talked about that here, is that they all form a 1 positive charge when they react. And typically what they're doing is they're reacting with halogens, which we'll talk about here in a little bit. And again, the reason being they always need to lose 1 electron to become stable, like their nearest noble gas neighbor. Solutions that are made with these elements are typically basic, which is another way of saying alkaline. So again, we kind of saw that here, where sodium and the hydroxide came together and formed an alkaline solution. But again, if we had something like NaCl or NaBr, those are also going to be considered to be alkaline. Excuse me. Some examples of alkali metals and their major uses. So lithium would be another, it's another family member. It's used to make batteries. It's also used to treat some mental health disorders. So lithium is found in lithium carbonate, which is a medication that's used to treat bipolar disorder. And nobody really knows, at least as of the most recent research, why this works, but it seems to do a lot of help. It brings a lot of help to folks who have suffered from bipolar disorder. Sodium is in table salt, which again, a lot of times we use sodium as our reference alkali metal because it's something that you guys are more familiar. And obviously table salt can be used for a lot of different things. It's also really important in biochemistry and in the way that our body works. So we have these sodium potassium ion pumps in our cells, which again that whole process helps to transport molecules into and out of the cell. And that's something that we learned about last year. Rubidium, cesium, and francium are all really super dangerous and typically will react with almost anything. And we don't use them because we value our fingers, we value our eyesight, we value just our overall health. And so typically, if you're going to see those being reacted, you're going to see those on videos with people who do pyrotechnics or somebody who has an advanced chemistry degree. So again, a couple of other things on here. They're never found as a free element, and I think that's really important. So in nature, you're not going to find these just free floating around because they're so reactive in the presence of water. And you're always going to find these with something else. In fact, the samples that we have that are considered, pure sodium or pure potassium, pure lithium, those have all been manufactured and then they're stored under mineral oil to prevent them from reacting with any sort of moisture in the air. Now, if you were to be casually, experimenting with that and you were to tip that over and it all spilled out onto a sink and you didn't clean it up, you could potentially have a explosive situation happening, if you had walked away and then it eventually became exposed to air. So we're typically pretty careful with that. As far as some of the physical properties of these, they are shiny. And it's interesting because just like anything, a lot of times they react with oxygen. So the outer layer of them, when you see them, will look dull, but then when you cut into them, they're super shiny and it's just kind of a cool thing. They're also very easily cut. So you can take a butter knife and slice through any of the ones that we have in class. You can actually, it's like cutting through, I wouldn't say warm butter, I wouldn't say cold butter. It's kind of like an in-between, maybe like the margarine that you might have in your refrigerator where you can cut through it with a little bit of pressure. They all have very low density, so when you are putting this in water, they are less dense than water. They kind of skitter around on the top surface of the water. And part of the reason why they're doing that, in addition to having a low density, is they're creating immediately that hydrogen gas. So like underneath them, they have this layer of hydrogen gas being formed, which also helps to keep them afloat. They have low boiling points. And as far as the rest of this information, they do have large atomic radii and then also large ionic radii. So they're some of the larger elements on the periodic table. But I guess of all of those things, I would say the shiny, soft, easily cuttable kind of things will be something that I could use in a phrase that would help you to remember what we're talking about. But the fact that they're some of the largest elements on the periodic table, that will become inherently obvious when we start studying those trends in the future. Our next family that we're going to highlight are the alkaline earth metals. And again, these are going to be your group 2 elements. So if you go from the left to the right across the periodic table, you're looking at column 2. Alkaline earth metals are like the alkali metals, except that their properties aren't as extreme. For example, they're very reactive, but they don't blow up in water. Calcium does, however, fizz a little in the presence of water, but it's not going to do like anything where it's gonna like all of a sudden explode on you. They have low melting and boiling points, but not really all that low in comparison to the alkali metals. They do form ions with a 2 positive charge, which reflects their, desire to lose 2 electrons to form a stable valence shell. So some of the more interesting alkaline earth metals, at least I think more interesting, would be magnesium. Magnesium is a strong and light element, and it burns like crazy when you light it on fire. I know that you guys saw this in 9th grade, but we'll go ahead and do this again. We actually will burn magnesium a few times. One, when you're just looking at properties of chemical reactions and kind of identifying what kind of reaction it is. So that'll be a really good example of a synthesis reaction. The magnesium will combine with oxygen from the air to form magnesium oxide. But we'll also use it when we're looking at some empirical formula work. So where we're trying to actually determine the true nature or true formulas, we'll use it then as well. It'll be a really nice little quantitative lab that you'll do. The element is commonly found in the rims of expensive sports cars driven by, oh, this is super funny. So I'm reading a statistic off of a website. It says, this element can commonly be found in the rims of expensive sports cars driven by middle-aged men having a midlife crisis. And I wouldn't say that's just middle-aged men. I think that's anyone who's having, a strong desire to drive cars fast and be fancy. So I don't think that's just a guy thing. The next one is calcium, and we know that calcium is found in our bones, and in fact, it's one of the elements, it's considered an essential element, and it's one of the elements where if our body isn't getting enough calcium, intake over the course of a few days, it'll start to leach that calcium from our bones, from our teeth and bones, and so we can develop different health issues over the course of time if we're not getting enough calcium. It's also obviously found in rocks. You guys studied a lot of different kinds of rocks in 8th grade, and calcium was one of those key minerals that are found in a lot of different kinds. Shells in the ocean, right? So organisms that live in the ocean that have shells, they're pretty much creating their shells out of a compound called calcium carbonate. And calcium carbonate is also what we use when we are writing with chalk on our blackboards, or probably more useful, we've been using it a lot in the summer, like writing it on the blacktop or the sidewalk, just kind of getting outside and doing some creative things. So that calcium carbonate compound that is what you're seeing in chalk is the same compound that marine organisms use to build their shells. Coral reefs are built with this calcium carbonate compound. So one of the things that's kind of tricky about that is calcium carbonate reacts with acids and it decomposes to form carbon dioxide. So interestingly enough, carbon dioxide, as we learned at the very beginning of the school year, when it combines with water, forms carbonic acid. and acids break down calcium carbonate. So it's just this kind of, once it starts to go, we have increased CO2 levels in the atmosphere that dissolves into the ocean. It decreases the pH, or we could say increases the acidity of our ocean. That acid is reacting with those marine organisms who, build their shells out of this calcium carbonate. Those carbonate ions are released out into the ocean, form more acid. So it's just kind of what we consider to be a positive feedback loop, although I don't think that the effects of it are necessarily viewed as being very positive. Another thing I want to highlight from this website I'm looking at, which the website I'm using for some of these additional facts, outside of my little side stories here, it's mrgooch.bringster.net, and he has a lot of really cool chemistry things. I'll try to link this alongside of the video as a resource for you guys to look at. So he actually talks about Marie Curie and has this to say. So Marie Curie was a super awesome scientist who won 2 Nobel Prizes for her work with radioactive materials. Unfortunately, despite her Rutherford level awesomeness, she was murdered by these sinister radioactive compounds, including alkali earth metal radium, and she died, unfortunately, in 1934. After her death, it was discovered that all of her possessions were so radioactive that people who wish to see them now even need special protective gear, and so it's still releasing radiation. There is a phenomenal book called The Radium Girls, and I think, as I'm kind of thinking through this, I'm going to post a link to that. It was a book that I had been introduced to by MJ Urey, so a senior this year, and he had been talking about this kind of really dark part of history, specifically with radium. And what we know about radium now is that it is radioactive and it glows in the dark. And so what it was being used for primarily was to paint watch dials so that they would glow in the dark. And initially, this was something that was used just for everyday common household item. But then it was also during the war, it was used for a lot of different instrumentation. So you could see the dials and you could see everything in the evening. Well, one of the things, and the Radium Girls is all about these women, these young women, teenagers to women in their early 20s, who would work at these radium dial facilities, and they would paint with this radium, and they were constantly covered, with it, exposed to it. But one of the things that was kind of insane looking back on it is that they would actually, as they're painting it with these tiny little paintbrushes, they would take the paintbrushes and they would put them in their mouths to form a fine tip, and then they would dip it into the radium, and then they would paint, dip, and then, or put it in their mouth, dip it, paint it, put it in their mouth, dip it, and paint it. So they were really gaining copious amounts of radium and taking that into their body. Well, when they started to fall ill, the companies were in complete denial that they had any sort of responsibility for these women. There's stories, the stories were just terrible. So there's stories of these women, they started losing their teeth, and their teeth would just kind of start to fall out and just break down. Because one of the things they found out about radium is it's like a calcium leach from the bones. And so it was breaking down the bones of these women. There's a story about this woman, she had lost quite a few of her teeth, and she went in and she was in terrible, terrible pain. So she went into the doctor to get, the dentist to get another tooth extracted. And what ended up happening when he went to extract the tooth is he ended up removing, he pulled a chunk of her jaw out. Can you imagine how horrifying that was? But at the time, even with this medical evidence, because these women were going to different doctors and the doctors weren't necessarily talking to one another, so they were noticing these odd, things happening to these women, but there wasn't, nobody else outside of these women who were working at the radium companies were coming in with these issues. And so the science was lagging, the medical community lagged on that, but the companies didn't take responsibility. So anyway, this book, The Radium Girls, goes over the history of it. And even in modern society, there's still denial of the wrongdoing that happened. So again, for those of you who are really curious about some of the historical things that have happened, Radium Girls is a phenomenal book to read, in my opinion. I believe there's also a movie. I haven't watched it yet. So the movie is obviously, it's a historical fiction, but it doesn't follow exactly the stories, whereas the Radium Girls, it's all interviews and interviews with family members of these women who unfortunately passed away, or interviews with some of the women themselves who were still around, are still around, looking at historical documents and so on and so forth. So again, just a really good example of one of the alkali earth metals and some of the historical context there. As far as anything else goes with things that you guys need to know, we know that they form cations with a 2 positive charge. They are also very reactive with the halogens. I want to clarify here, just because I didn't highlight that 2 positive cation thing, I'm not highlighting it because I think it's something that you already know, right? Or it's something that if you were to look on the periodic table, you would already know that. The other thing is it also reacts strongly with water to form alkaline hydroxides and hydrogen gas. So again, it's one of those things, just like alkali metals, when calcium, for example, so we have Ca, has 2 valence electrons, and it comes into contact with water. This reaction happens more slowly, right? I'm gonna think of water as being hydrogen with a plus and OH with a minus, just to make this a little bit easier to understand. So what's going to happen is that this hydrogen with a positive is going to take an electron away from calcium. One of the reasons that it can do that is hydrogen's nucleus is actually stronger than calcium's, okay, and it's going to then, transfer over that positive charge. So this is going to come over here. Well, we would know that, okay, that's reaction's done. So what we're going to need is another water. Again, same thing's going to happen. This new hydrogen is going to come along and steal away that calcium electron, and then the charge transfers over. So then we've got this hydrogen. Well, from the previous thing, we know that these are going to come together to form a bond, and that's going to form hydrogen gas. A reminder that this reaction happens slowly in comparison to this actually being an alkali metal. And then what happens is that this calcium ion, so now we have a Ca with a 2 plus, can then form a bond with these 2 hydroxides. So what we're left with is CaOH2. Super important that that OH is in parentheses because we have 2 of them. And then we also have that hydrogen gas. All right, as far as anything else goes here, for the physical properties, shiny, silvery white in color typically, relatively low densities. They're more dense than the alkali metals typically, but again, relatively low densities, melting points and boiling points. And everything we're doing is comparing that to actual metals of, like copper and lead and gold, mercury, those types of things. Our next section is looking at what we call the transition metals. And interestingly enough, we could actually incorporate the lanthanides and actinides, or we call it lanthanoids and actinoids, into that lump or into that category. So when we're talking about transition metals, we're talking about the D block elements and then F block elements. So we consider the D block elements to be the the outer transition metals, and then the F block elements are referred to as the inner transition metals, but nobody really refers to them that way. And so typically if we're talking about D block elements, we just blanketly say transition. And then if we're talking about the 4F group, then that's going to be our lanthanide, and then the 5F group will be the actinide. So really just simple terminology there. So some things that you guys should know for and we'll just kind of go down the column here. So with the transition metal, and we've already talked about this, they are paramagnetic if they have 1 or more unpaired d orbitals, okay? And the ones that are diamagnetic are the ones that are fully paired. So, we can kind of look at zinc and cadmium and mercury being those completely diamagnetic, but most of them are paramagnetic. Again, a reminder from the previous lesson that the more unpaired electrons that you have in the d orbitals, typically the stronger the attraction to a magnetic field we actually see. Now, these are our standard metals. When we think about metals, most of the elements, that are in here, what we refer to, like these are the things that we think about as being metals. So like gold, mercury, silver, zinc, copper, nickel, iron. So they have high densities, high melting points, high boiling points. Every single one of these, with the exception of mercury, is solid at room temperature, right? And it requires a lot of energy to actually get them to change phases. Most of them are malleable. Most of them are ductile. Most of them are good conductors, although we know some of them are better conductors than others. And they typically are hard. Some of the major chemical properties are that they'll form multiple cations due to their valence electrons being present in multiple shells. And what I mean by that is we have, most of them are going to have an S block, and then they have the D block. So the S block electrons get taken, and then the D block elements can also then start to be removed. So that's what I mean by having their valence electrons in multiple shells. So as soon as you remove the S shell, we go down to, the next level, and then we're removing from the D block in that level. Those are some of the big things for those transition metals. The lanthanides, these are your rare earth elements. Again, like the other ones, they have high densities, high melting points, high boiling points. They typically have large atomic radii or radiuses. That's why I would say radii. Okay, used in lamps, lasers, magnets, phosphors, motion picture projectors. They're commonly used. They are silvery white metals similar to the alkaline earth metals, and they are also relatively soft. So in comparison to some of the, a lot of the upper transition metals, they are softer in comparison. Now, these can also form cations with varying charges, but several of them form the 3 positive charge. They will tarnish when they're exposed to air. They're very reactive with water. So this is, again, another example of elements being highly reactive with water. The transition metals we just talked about, very low reactivity with water there. They can tarnish, but it's not like they're going to react with water and form something explosive. They burn easily in air, and they're also strong reducing agents. They will fluoresce under ultraviolet light, which is pretty cool. And then the last ones, the actinoids, these are going to be very dense metals, and that's kind of the key physical property I think that we really need to know. They're radioactive and they release energy upon decay. So if you look at that row, it's actinium, thorium, uranium, neptunium, plutonium. So as you're reading across those, some of those probably sound very familiar in terms of radioactivity. These also share the property of tarnishing readily in air. They will react with boiling water, so the water has to have a lot of energy in it, or dilute acid to release hydrogen gas. Again, that's an important one. And they will combine directly with no metals. So some of the elements can form compounds with other metals. These ones do not react. All right, so looking at the website, I'm going to just see a couple of other things that he has brought up here. So with the D block transition metals, he talks about what I've already talked about. We talked about this earlier. Another point he brings up is that iron, nickel, and cobalt are all magnetic. Again, we talked about ferromagnetic materials. And just one really quick thing on that. Ferromagnetism allows the substance itself to be magnetized. So it will hold a temporary magnetism. So you can take iron, run a really strong magnet over it, like an iron nail, run a really strong magnet over it, and then it can pick up other nails. That's ferromagnetism. And so cobalt and nickel also can do that. He says on here, transition metals are used to make practically everything, which makes sense. Looking at a few other things. Oh, this is an interesting thing too. So lanthanides are used in optical coatings such as shiny sunglasses and other lenses, while we know that the actinides are used in nuclear power plants, atomic bombs, and even smoke detectors. And that would be the biggest thing I guess I would want to talk about with respect to the lanthanides and actinides. Really, a couple big things there, just know where they're located, and then also just some of the key properties. All right, as we are wrapping up our notes on the different groups, we're kind of over in the P block now, looking at elements that we would classify as the semimetals, the halogens, noble gases, and then hydrogen. And then amongst this are going to be some of those groups that we had in there, the post-transition metals, so the elements that are not classified as any of these things, and then also the other non-metals. And again, each one of those has special properties and has special things about them, but we're going to kind of focus in right now on the actual families. So the first group that I want to talk about just a little bit here are the semimetals. And again, these are going to be those elements that kind of fall along the staircase. And so we have bismuth, silicon, germanium, arsenic, antimony, tellurium, and then polonium. Now, some resources will also put astatine in there with the semimetals, and one of the reasons they do that is because astatine does have some properties that are more characteristic of a semimetal than they are of the halogens. But for the purposes of recognizing that the fluorine, chlorine, bromine, iodine, and astatine group, they all have 7 valence electrons, all highly reactive. I kind of like to keep them labeled as a halogen. So we're going to leave astatine off of our list for in here. And again, depending on what chemistry resource you look at, some will list it as a semimetal, some will not. So we're good. I've double checked. All right, some of the major physical properties, these semimetals typically have behaviors that are kind of inner between the metals and nonmetals. So an example of that is like silicon possesses metallic luster like a metal, but it's actually brittle and considered to be a poor conductor. So, most metals are malleable and they're good conductors. Silicon does not have those two properties. So boiling points, melting points, and densities of these elements vary greatly, and it's hard to give like just one, classification of a physical property amongst that group. For their major chemical properties, similarly, reactivity varies greatly depending upon what it is reacting with. Also, if we look at, boron has 3 valence electrons, silicon has 4, germanium has 5, germanium also has 4, antimony has 5, tellurium has 6, and then polonium also has 6. So depending on how many valence electrons they actually are going to determine kind of how they're reacting. Are they going to form cations or anions? How many electrons do they need to stabilize their valence shell? Boron will act like a nonmetal when reacting with sodium, but it will act like a metal when it's reacting with fluorine. What I mean by that is if it's reacting with sodium, then it potentially could form a negative charge, And then if it's reacting with fluorine, it can form a positive charge. So that's just like an example. Again, boron's going to kind of do its own thing, and it will be something that we come back to as an element in the future that is a rule breaker when it comes to its valence shell. Again, one of the things that these are used for, the semimetals are used as semiconductors. If we jump over to the halogens are one of my favorite groups just because they're all unbelievably reactive. Fluorine is the most electronegative element, which essentially means it has one of the strongest nuclear strengths, and that can still pull electrons. And so it generally will instantly strip electrons off almost anything it comes into contact with. And the other halogens pretty much do the same thing, but as you go down the group, they aren't quite as strong. The further away that valence shell is from the nucleus, the less it is capable of actually like adding electrons to it or stealing electrons away from other things. So these elements are also pretty good at killing living organisms, which can be both good. Like if you're using it to kill contaminants like living organisms in the water, that's a good thing, but also bad when you're using these as chemical weapons, right? So overall, it's usually advised to stay away from these chemicals unless you've got a pretty good reason to interact with them or to work with them in your research. And when I say these elements, I mean the ones that, you don't want to just work with chlorine gas just as a daily occurrence. All right, a few other things here. Again, similar to some of the other things we've talked about, their properties, the physical properties can vary greatly. We know that iodine is solid, but fluorine and chlorine are gases at room temperature. So again, we can have different states. Even bromine is a liquid at room temperature. So we see 3 different phases of matter within the same family, which is not very typical. They're highly reactive with the alkali and alkaline earth metals. That was something that we had talked about before. And they will form those 1- anions. And then something else we talked about before already was that they'll form acids when bonded to hydrogen. Or maybe we didn't talk about that before, but we will be talking about that again. Noble gases, again, if you think back to everything you've learned, you remember the octet rule, and all elements wanting to or needing to gain or lose electrons to get to the same number of electrons as their nearest noble gas. And essentially this is just saying that these elements are stable and typically unreactive. Noble gases are used for a whole bunch of things. What these uses have in common with one another is that they require the gases that are being used to be completely unreactive. With respect to some common uses, argon is one of the most commonly used noble gas, and it's found between panes of glass in fancy windows and in glove boxes where air-sensitive chemistry is actually occurring. That is not something that I actually knew. Okay, one of the things that we say is that they are non-flammable. Okay, so although these are gases and a lot of the gases that we encounter potentially are flammable, these are all non-flammable and again, typically unreactive due to having a full valence shell. Gases at room temperature, which means they have low densities, low melting points, and low boiling points. They're colorless, odorless, and tasteless. So the color that you're actually seeing when you look at a neon sign is simply you're running an electrical current through that gas. The electrons there in the gas are being excited to higher energy states. When they fall back down to their normal ground state, they release photons. So those photons of light, that's what you're seeing being emitted. And that's, that you don't see that when the gas does not have an electrical current running through it. All right, the very last one that we need to talk about here that is like an official family or an official by itself kind of thing is hydrogen. A few physical properties. We know hydrogen is gas at room temperature. It has an incredibly low density. In fact, because of its low density, it was used for a while in airships to get the airships, or that we call them blimps, to rise off the ground. I found this very interesting. So melting point of negative 259.1 degrees Celsius, and then the boiling point at 1 atm is just slightly above that, right? Just like slightly warmer temperature at negative 252.9. So we know that hydrogen has 1 valence electron, and its most common form would only have 1 proton and 1 electron. So the most common isotope doesn't have a neutron. It is capable of forming either a 1 positive charge when it is interacting with some of the nonmetals, or a 1 charge when it interacts with some of the metals. So for example, if we put calcium with hydrogen, it'll form calcium hydride, and that has a formula of CaH2. But if we put hydrogen with something like fluorine, it forms HF. So again, it just kind of depends on what it's reacting with, what charges it can potentially form. We also know that hydrogen can share electrons with other elements. So its nucleus is fairly strong for such a small element. And actually maybe because it's such a small element and it just has 1 electron to kind of take care of, it does a nice job of being able to share that electron with other elements whose nuclear strengths are fairly compatible. Carbon would be a good example of that. Oxygen would be another good example of that. Really important thing too is that it forms acids when combined with halogens. I know I said that kind of earlier in this video. So if it combines with fluorine, it forms hydrofluoric acid. If it combines with chlorine, hydrochloric acid. HBr will be hydrobromic acid, HI, hydroiodic acid. And so those are some common acids. I would say hydrochloric acid being the most common one that we actually use in our class. And anytime that you have that hydrogen out in front of the molecule like that, you can classify it as an acid when it is in contact with these halogens. The last thing I think that's important here is just that it forms a diatomic element when it's by itself. I know we talked about that previously. So we've got a hydrogen with one electron, another hydrogen with one electron. Because it would be the exact same nuclear strength, they would share those electrons and it forms H2 gas. And if you haven't been living under a rock your whole life, you know that hydrogen gas is inflammable. The most classic example of that would be the Hindenburg disaster. And I'm going to post a link to a video that actually talks about the Hindenburg a little bit more as part of this lesson. All right. So that's all of the information that I need you to know. Again, there are some elements that we didn't cover, like carbon and nitrogen, oxygen, sulfur, those kinds of things. I know we have covered them quite a bit in biology. We talked about them exclusively when we talked about the molecules of life. So for the purpose of inorganic chemistry, we kind of focus in on these other elements. All right, please feel free to ask questions kind of as we go through, once we come back from break and whatnot, we're going to have an opportunity to kind of look back at this information. And if you have additional questions, please feel free to ask those. The idea behind this is you understand now a little bit better, or you now remember the different locations of the groups, and then you just have some additional background knowledge on the major properties of some of the key groups on the periodic